Okay, as I said in the previous, towards the end of the previous video, we now will be looking at several examples of how whatever we have learned over last 7 weeks and in the last video kind of summarize that, how that is applied in real world situations. So, let us look at the first example. This project is it was a project, it was a funded project which we were at that particular time. It's not that old, it's almost 2.5 to 3 years old project. I was working in Southern Ontario as a faculty at the University of Guelph, and this is a master's thesis of one of my student. So that's this is from a funded project. So in this project there was, as we have talked about earlier, composting is used as a means of treating organic waste. So when you do compost, if you do it 100%, composting is an aerobic process. But if you when you do the composting, what happens is there will be pockets of anaerobic activity going on, and that anaerobic activities leads to some fall gases being produced, and that creates odor problem, that creates the smell problem. So in this particular project, we were looking at what are the different, in terms of the different odor control technologies which is out there, how they compare from the technological perspective as well as from the life cycle perspective. So there were two parts. One was the technological perspective, other is the life cycle. The life cycle is which is kind of relevant for this particular course, but I also left the technological part there. We'll kind of go over that a little bit quicker. Kind of it will give you a good idea of how you select a technology. Say if you have to make a selection of a technology, how you go about that. So let's look at this particular example. So we'll look at the technological and life cycle. So here there were in this particular we were trying kind of talk about the introduction, which we already kind of did. Then why order is still a problem, what is the issue with the order, what is the objective and scope of the project, what are the technologies out there. Then we will have the key findings of the technological assessment. Then we go into this LCA part. If you remember from that LCA, if you look at from the step 7 until 11, 6 to 10, if you goal and scope, system boundary, assumption limitations, data inventory, LCA results. So these were the core of LCA steps that we mentioned earlier several times in the course, and then we will have the discussion and conclusion and recommendation. So municipal solid waste, as in India also we have been trying to, if you look at the new MSW management rules of 2016, the government is suggesting that we should have a source separation of at least food like a wet and dry. Wet, when we say wet, it's mostly organics, it's the food waste and other organic component of that. This project was done in Canada, in southern West Ontario of Canada. So there they were doing wet and dry separation where food waste was collected separately. So here in terms of the food waste, they were nearly 40% of the municipal or the residential waste stream, and they were having a organic waste processing facility, either using composting or anaerobic digestion. So there has been composting. When we do the composting, the odor is a problem, of course, same with the AD facilities, and there have been cases where complaints from this compost facilities had led to certain lawsuits. Or London, Ontario, which is around, you can say, around 3 hours drive from Toronto, and there they had a issue of they had to pay, actually spend several $100, several thousand dollars, like a couple of $100,000 to fix their odor control system because of the complaint from the nearby facility, and some also leads to the closure of the facility. So this odor control is is one of the important aspect in the organic waste management, and it's expensive and also environmentally impactful component. So we wanted to look at environmental impact in terms from the LCA perspective. So we need to have a good understanding for odor control. So there are what the source of odor? Hydrogen sulfide. Again, if it's a reducing condition, you will have hydrogen sulfide, organic sulfur, organic sulfide, ammonia, amine, fatty acids, aromatics, methyl ketone, tarpene. So these are major ones which causes some sort of odor, some sort of a smell. So this is because of the reactions taking place. So the aim of this project was twofold, as I said earlier: identification and technological assessment of the odor control technologies, and then life cycle assessment, and based on the phase 1 results. We did a life cycle assessment of the selected odor control technology. So, in terms of the technological assessment, what we did, there are several order control technology methods are out there: biofilter, activated carbon, packed bed wet scrubber, fine mist, thermal oxidization chemical, masking agent. So, there are lots of order control things are out there, but we cannot I cannot go over each one of them in great detail in this particular class, but we will give you a kind of brief overview. So, biofilter, what it does, it uses microorganisms to degrade and destroy order compounds. So, it uses certain microorganisms, and so here you have fall air coming in, passes through this, that is the bulk media filter bed. So, here we have perforated support plate. So, this it will go up, and then you have the water sprinkler to moisture the filter. So, because as you know, any microorganism, they like a little bit moist environment, and then you have this exhaust air which should be clean, and then even after this it will go to the chimney, and then it will go out at a higher level. Activated carbon, it is removed by adsorption. Activated carbon used a lot in so that can be used as adsorption. Activated carbon can have a surface area of close to 1400 meter cube per gram. So, that is how we used for activated carbon. So, that is also used for removing of order chemical. Packed bed fine wet scrubber, what it does, it washes odorous compound from air stream into liquid scrubbing solution. So, here you have like a makeup, this is your spray, here chemical solutions are coming in, packing media, and makeup solution is spent chemicals, screen is over there. This is the recirculation tank, this is the packing media. So, you have this odorous like a fall odor carrying gas into the system, and then it goes through all these different steps, and then you have the treated air coming out. So, there are other systems are out there, thermal oxidizer, chemical oxidation, masking agents. So, there are lots of different chemicals out there which works on different principles. If you end up doing some research in this area, you can go and learn more about it, or if you are interested to learn more about it, you are always you can find information about that. So, in terms of technological assessment, when we say technological assessment, what actually we are trying to assess? How to do this technological assessment? Anything when you try to do, you of course you look at the what will be the cost, what is the capital cost, what is the operational cost, what is the maintenance cost, what will be the volume of airflow that it can treat. So, what is the capacity, what it can treat for, and how much order removal efficiency, how much order can be removed, reliability, long term performance, the space requirement, chemical and media usage, how much energy will be required, how much water will be required. So, all these different factors you can look at. So, this is exactly what we did. So, for this, as you can see in this table, we looked at for different types of technology, biofilter, activated carbon. So, all these things that we listed, we looked at the order unit removal, capital cost, operation cost, reliability, space, energy, chemical, water usage, and all these data was basically from different reports and literatures and other things out there, because we had to kind of rely on that, and we come up with this particular comparison table where you can look at different categories, different types of technology based on their different categories, how they are behaving. So, based on this, from a technological perspective, if you look at the table again, biofilter came out to be the preferred option. So, the biofilter was based on technological efficiency, usability, cost perspective, biofilter came out to be better. Packed bed wet scrubber also functioned well in the composting system, especially for more concentrated air streams. Fine mist wet scrubber are not a preferred choice due to higher capital and operating cost. Carbon adsorption can be useful, but its applicability is limited to order streams where ammonia is not produced. Since ammonia is produced, it doesn't work very well with ammonia. Thermal oxidizer is not practical because of high cost, use of fossil fuel, SOx and NOx production. Oxidizing agents and masking agent can be used as a part of, but they are not effective as individual methods. So, you can just have kind of a combination with others. So, based on this, we looked at this packed bed wet scrubber and the biofilter. So, those two we chose to go for LCA. So, we used in terms of biofilter, we had two types of biofilter, which is a synthetic media biofilter and a wood chip media biofilter, and then we compared, and then we had the packed bed wet scrubber system. So, we took these three technologies. The reason for taking these three technologies was also because of the area that we are working with, the funding agency who has funded the project, they wanted us to look at synthetic media biofilter and wood chip biofilter, because the way the system works over there, they basically the different municipalities, they give some money for research, which goes to a big pool of money, and from that big pool of money the research project is funded. But the research project should be kind of an applied research, should help these municipalities. So we had this Guelph, which was city of Guelph and the Peel region. They were using synthetic media, while Hamilton and London were using organic wood chips media, and all these are in southwest Ontario in Canada, in province of Ontario. So both system has similar odor removal efficiency, which is a packed bed wet scrubber system. So based on that, we use these three technologies for comparison. So in terms of life cycle, it started from the goal and scope. The LCA will take into construction, include transportation, energy usage, water and chemical usage, landfilling, recycling, whatever we need for the decommissioning phase. We use the CIMA-Pro 8 software. You don't have to use this software, but this is one of the software which is very commonly used, and the EcoInvent database. One thing I would like to let you know, that as a non-OECD country, in India, if you are working on LCA exercise, EcoInvent database is actually available to us for free in academic setting. So you should be you can be able to get the EcoInvent database. And even if you are not using CIMA-Pro, there are some open LCA. So there is another one which is open LCA. You can use that open LCA software with EcoInvent database. So because CIMA-Pro is a bit expensive, but it's not that bad either. It's a very good software. So all these three technologies we looked at over a 15-year period, which is a kind of a life of a synthetic inorganic media based on the talk we had. So then we had to remember what we said. You have to have a system boundary and a functional unit. So the system boundary is considered to be the region of Ontario. That's where we are, geographical boundary. And the facilities boundary of each system only includes the odor removal system. So we don't consider pre-treatment or pre-scrubbing of air, because our goal was to look at the environmental performance of this odor removal system. And since three systems have a comparable odor removal efficiency, effect of treated air is not considered. We assume that all the three will have similar. And facility in Guelph was treating 30,000 tons per year for organic waste. Facility in Hamilton process 70,000 tons per year for organic. All material, chemical and water energy usage for all system is scaled to 1,000 tons per year. So what does that mean? Our functional unit is treatment of 1,000 tons of organic waste per year. So, and we collected data from Guelph and Hamilton. So it was a real data. So the real data was collected, and then we scale it down to 1,000 tons per year. So that's how it has been done. So data for biofilter was collected from facility in Guelph. Synthetic media, Hamilton uses wood chips, so we got the data from there. So for packed bed waste scrubber, we could not find a system nearby where we could go and collect the data. So we collect the literature data and previous studies, whatever the previous studies were out there, and again scale it down to 1,000 tons per year. So so there are certain assumptions, as I said earlier as well. You may have to make certain assumptions, because otherwise your LCA becomes so big that you cannot deal with that. So only material, chemicals and equipment with significant quantities were included in this study. Small components such as screws, nuts, bolts, wiring, etc. were assumed to be negligible effect. In terms of scaling data, it was assumed that economy of scale have limited impact, so negligible impact. So that was a basically linear relationship. It was assumed that the treated air based on 1,000 tons per year would have negligible environmental effects, which compared to the effect of material, energy, water and chemical usage. Reasonable assumption based on common knowledge were made in terms of any missing data. The database made use of European and world values. We didn't had the local Canadian values, although we did change the energy mix, and we used the energy mix of the Ontario, southwest Ontario. So key data and inventory. Biofilter system were divided into 5 sub-assemblies: building frame, biofilter media, fan suction system, water sprinkler system, control and monitoring system. Similarly, packed bed, we had the outer cell, packing material, spray solution, fan suction method, control and mitigation. So from there, we had looked at the facilities that we saw. Guelph has a 3 concrete cell, 3 suction fan with 810 meter cube of synthetic media, which is silica and aluminum coated with a mixture of ferrite, organic carbon, alkaline buffer and hydrophobic chemical. In Hamilton, we had 1 big concrete cell, 4 fans and 1200 meter cube of wood chips, which are changed every few years. And in packed bed system, fiberglass and Seattle packing system, sodium hypochlorite, sodium hydroxide was used as a scrubbing chemical. So, and we use 12 impact categories rather than there are other impact categories out there as well, but we use the 12 impact categories: cumulative energy demand, climate change, human toxicity, photochemical, metal depletion, fossil, terrestrial acidification, freshwater, marine eutrophication, terrestrial ecotoxicity, freshwater ecotoxicity, marine ecotoxicity. So, there are all these impact categories we used. So, if you look at the LCA result for in terms of cumulative energy demand, direct and indirect, what you see is this is the packed bed wet scrubber system, this is the biofilter system wood chip, this is the biofilter system inorganic. So, more energy is needed there, and in these graphs what happens is whatever is needed the most is made as 100. So, whichever has the highest kind of impact, we take it as 100, and based on that 100 we put these values, the other two values are shown based on that particular 100. So, that is why you will see always one graph kind of goes all the way to the top. So, if you look at the breakdown of that inorganic biofilter CAD, cumulative energy demand, it is electricity, high voltage electricity, that is the major one. Then we have aluminum sulfate, concrete, which is the blue one, blower and heat exchanger, polyvinyl chloride is the yellow one, blower and heat exchanger is the white one. So, this is all, and this bottom one is actually green. This green one is what we have is aluminum sulfate, and the top one, which is the light gray, is the remaining processes. So, you can see the electricity, the high voltages, that is the one most dominating. Same thing with the wood chips too. This electricity is which is the most dominating in terms of its cumulative energy demand. Breakdown of packed bed CO again the electricity usage is the number one kind of number one like impact. So, we try to remember from the previous video where you have to characterize. So, you have to scale the result by percentage based on highest impact, and then you have to normalize. So, divide the impact category by the reference. A reference value we can find at the average environmental load in a country. So, reference value can be found by looking at the average environmental load in a country over a year and divided by the number of people in that year. So, this is the total based on 100. We have this climate change, human toxicity, different impact categories. The red one is the packed bed scrubber, the green one that you see over there is a biofilter wood chip, and the yellow one is biofilter inorganic. So, biofilter inorganic comes out to be the kind of the maximum impact for all these categories that have been listed here, and followed by biofilter system, wood chips, and packed bed comes out to be much better, but again it is costly. And if you normalize that based on as you can see this metal depletion in this biofilter system because of the usage of ferrite and others metals, that comes out to be much higher impact as opposed to the other impact, but again it's comes out to be some sort of impact. In terms of the photochemical oxidation formation, both the biofilters are showing similar impact. Other categories: terrestrial acidification, eutrophication, ecotoxicity. Again, you can have the similar graphs showing up in terms of the different impact categories. Again, if you put it in actual values, you see the different impacts showing up. What it shows is freshwater eutrophication, you see more impact; acidification, you see more impact; eutrophication, terrestrial ecotoxicity, the impact is much less. Marine ecotoxicity, you see higher impact. So, in terms of the figures, the impact of concerns are metal depletion, just a summary of that: metal depletion, fossil depletion, human toxicity, freshwater eutrophication, and marine ecotoxicity. So, these 5 categories where we saw some sort of concern. So, if you look at synthetic biofilter LCA bag, if you look at the breakdown of that, where the major impact is coming out in terms of different. So, building frame is the red one, fan suction system is the green one, SCADA system is the yellow one, and then blue is the synthetic inorganic media. So, in terms of the metal depletion, so synthetic inorganic media is kind of leading that pack, and some in the freshwater ecosystem eutrophication and human toxicity as well because of the metals possibly. Then faction suction system, because of the electricity usage, you see that the green one is kind of the other big component which is showing in terms of its impact. So, So that kind of gives us some idea about where is the problem. So if we can do something in terms of the suction system, if we can improve that suction system, our footprint will go down. Wood chips biofilter, again similar stuff. You can see we had majority impact is the green part of the bar, which is your fan suction system. So the fan suction system is kind of the major one that you see for all the three categories. Here also the green one is the fan suction system. So and the gray one is chemical spray system, which is needed for packed bed. So both shows significant impact. Yellow is the SCADA system, which we see over there as well. So in terms of the climate change impact, climate change impact is low, but it is considered since always a concern. Fan suction system is responsible for climate change effects for all three order removal. Electricity demand is actually the main thing for the fan suction system, is responsible for more than 80% of the climate change. So it's the electricity, the kind of electricity that we want to use. Metals and fossil fuel, again the fan suction system. The metal depletion, fossil is a contributor to fossil fuel for all three, especially because 24/7 electricity usage is there. Metal depletion impact of wood chips and packed bed system is fairly low. Synthetic biofilter, you see high impact because of metals being used. More than 90% of this impact is associated with ferrite used in manufacture. Freshwater eutrophication, we have inorganic wood chips have a fairly high freshwater marine ecotoxicity impact. The major contributor is 24/7 electricity usage. Human toxicity, we have packed bed wet scrubber system, which is there is a higher than the fan suction system, contributes 49%, and the chemical spray system contributes 30%. Is SCADA control system contributes 80% of the impact. And so here again wood chip biofilter, major contributors are fan suction system, building frame and wood chip media. Inorganic biofilter, major contributors are fan suction system, inorganic media and building frame. So it's kind of similar, if you look at the proportionally, it's a similar type of effect is coming from each of these systems, but the level is a little bit different. So for the all impact categories, the inorganic media biofilter had the highest impact, followed by the wood chip biofilter system. The packed bed system had the smallest impact of all categories. Synthetic media showed higher impact level than wood chip media, even though synthetic media has a lifespan of 15 years and wood chip media had lives to be replaced every 2 years. Wood chips are expected to be composted at the end of life. Again, that's what it has been assumed, while the synthetic media will be landfill. Synthetic material has a material intensive manufacturing process, so that also leads to kind of the problem with that. So major contributing factor for all impact categories was the high electricity usage. So if you can somehow reduce the electricity usage, that will reduce the environmental footprint. So as an engineer, what is the take home message? The take home message we have is this energy usage is the big deal in terms of all these processes. There are other environmental impacts associated with other things there, but energy usage is one of the key stuff. So if we can come up with renewable energy, more greener source of energy, that will help us reduce the environmental impact. Biofilter system have to draw orders air through the large surface area, which is a single industrial fan. Inorganic media and biofilter primarily cause the high metal depletion impact. So in terms of conclusion for this particular study, what we found that choosing system based on operational parameters and biofilter system were recommended choice. Looking at the operational and maintenance and ease of operation, inorganic system is preferred over the wood chip because media doesn't have to be changed that often. In terms of system with lowest environmental footprint, clear choice was packed bed system based on LCA. Thus, the choice of the system depends on what criteria is important: cost, environmental impact, or system operation. So we suggested this particular kind of matrix over here. So there are different systems out there, as you can see: biofilter, inorganic, organic, and packed bed scrubber. And you have to look at the cost. See, environmental impact is a very, very important parameter. This whole exercise of LCA is to find out the environmental impact. So whatever the data you see over here is based on the LCA exercise, where we got the packed bed wet scrubber as number 1, then biofilter organic is 2, and biofilter inorganic is 3 in terms of the ranking. But it's not only the environmental impact when you implement a project. You look at the cost of the project, you also look at how does the system operation, whether you will be able to run that system, whether you have the manpower to run it, how sophisticated the system is. So all those, how easy it is to operate the system. So those things does come into picture when you finally decide. So here in terms of cost, biofilter organic comes out to be number 1, then biofilter inorganic, and packed bed scrubber is very costly, so that says number 3. In terms of system operation also, packed bed wet scrubber actually comes out to be number 3, which is and 1 and 2 is shared between inorganic and organic biofilter. But in terms of environmental impact, biofilter organic, biofilter inorganic comes out to be number 3, organic is number 2, and packed bed waste cover is number 1. So going by the different criteria, if you look at it, seems like the biofilter organic seems to be the most preferred one, because that's got number 1 in cost and number 2 in both system performance as well as the environmental impact. So that has the highest ranking. So it will be, so that's kind of gives us some idea of about the picture. So of course you need to look at the more detailed cost assessment, and also if we can look at the method of making biofilter system less energy intensive. And since a sizable portion of environmental impact is associated with the fan suction system, if we can come up with that process, that will really help. So that's kind of a summary of, this is one particular case study of how it is being done. So this basically gives you an example of how an LCA exercise is conducted. So now let's quickly look at another example, a small example, and then we'll kind of close this particular video. So for the other example, which we'll possibly look at, is comparing this kerosene lamp versus solar lamp. So if you are doing a kerosene lamp versus solar lamp, try to compare these two. We are using kerosene lamp, which is used in India or in lower like in our rural areas, but we are also, solar lamp is coming up. So how they compare, and we kind of, this was again, this project was done by one of my student, who is Brian Camanjoli. This is his slides. I'm just presenting it to you. It is he did a project with me on this particular small project. It's a undergrad, it's like a BTech thesis project, where he compared this kerosene lamp and solar lamp. So the goal was, again, the goal is to compare the kerosene lamp with the solar lamp and determine which one is the favorable option. And so again, we have to have a function and the functional unit. The function was to provide adequate light for reading and writing. Functional unit, we choose 100 lumens, 4 hours of everyday usage per 4 hours of everyday usage for 10 years. So that was in terms of like a function and the functional unit. Then you have to have the scope, and the scope, you start with the raw material acquisition, you go for the material processing, manufacture, assembly, use and service, retirement and recovery, and treatment and disposal. We didn't go to that part. So we did a cradle to gate. So this was he did a cradle to gate study. So this was the different component. So since this was this particular solar panel, that we solar powered lamp that we used, it had different components. Different components were not available, like what are the different components out there. So what he did, he took a solar this particular one, took it apart and looked at the different components, and tried to quantify what are the different components out there and what are the different materials present there. So then assumption was useful life 10 years, assembled in Shenzhen, China, distributed in Tanzania, Africa. So we kind of use that part as well. So transportation cost will be involved. So polypropylene, it's coming from Mitsui and Company Limited from Japan. Then we had polyethylene coming from Sangdong in China, which was producing this polyethylene for that. And we had a polymerization where polypropylene and ethylene will mix together, and hexane and co-catalyst. So there will be polymerization being done. Then we have printed circuit board, which was done by Junhai Vastbit Technology Limited. Again, this was kind of a real project. We had this solar lamp, we knew the solar lamp being produced, and these are where all the different sources are coming in for producing it in that. Then photovoltaic cell, which is produced again in China, Kingdom Solar Energy Technic Company. Then we had this LED, which is again Shenzhen, that's where Guangdong in China, which was Shenzhen Eastern Battery Company Limited, which is nickel metal battery. That was the LED as well as the battery. And then we looked at the impact for the different categories. So we took all these materials. So you look at the inventory. We found out what are the different materials. We also had where all these different materials are coming from, so that we can have the transportation factor included, because from the plant where it is being processed. So then you put all this information in this life cycle analysis software, and you start seeing all the different types of emissions coming out. Here on the bottom, on the y axis, you see kg of contaminants, and on the x axis you see carbon dioxide, CFC, PM10, U235, and all those different emissions that is coming out. So that's your impact from the processing material. Then you have the impact from the transportation. So this is showing you the transportation kind of cost. So the transportation, again we looked at PCB, PP, popular polyethylene, what are the things coming out. We have the land transportation as well as the water transportation and ocean freight liner as well. So based on this, how much mass, what's the distance it is traveling, what is the ton kilometer, and from there we kind of calculate what would be the impact of transportation. As you can see, more and more impact is actually coming from the transportation side for the different type of impact categories. Then we have processing, metal working, where injection molding, assembly, packaging, cardboard. So those things are being made. So this is in terms of what is there, metal working machine stuff, how much kg of CO2, so different types of metals. So we looked at the different impact categories. So this particular graph kind of shows you different types of impact categories from the machine, the operation for the steel, the metal working machine. Then similarly for injection molding, what kind of impact is there from the injection molding side for the different categories. And then it has to kind of transport it to Tanzania, and there it will be looked at. So there is a transportation. So in terms of transportation from China to Tanzania, what are the impact categories, how much is the impact, we try to quantify that. So then you take it to, again, different types of impact categories from the battery, for the different types of battery, circuit board, solar cell, LED, polypropylene, cardboard, polystyrene, polyethylene, all the things that is out there, we kind of looked at their stuff. Then we had that's for the solar lamp. For the kerosene lamp, we are using it's a 2-year usable life. And we have a wick. We use as a recycled material, and it is developed in Nairobi, Kenya as well. Is no transportation, that much transportation involved. So it's 10 grams of woven cotton wick, 655 grams of tin container, 5.5 liters of the capacity, then the kerosene fuel used for that. So in the transportation, a little bit of transportation which is involved from the plant to the site, and this it kind of shows this much kilometers, and this is the ton kilometers we have calculated. And then for similarly, we have looked at the environmental impact categories for all this different impact from the cotton wick as well. What could be the potential impact? Again, CO2 emissions was the number one. Kerosene fuel as well, we saw the impact, and for the kerosene fuel, we see that different types of impact that is coming out. It's fossil depletion is actually the kerosene. Since it's a fossil depletion, it comes out to be much higher. So the different impact categories for the kerosene lamp, again the fossil depletion and the other categories, they show up as the higher impact categories. So these are again we look at the cotton wick, kerosene lamp, and the transportation, how much is the impact coming out. So it's how much they will be used, how much kerosene is used, a lump of kerosene used per functional unit, what is the density, and all those calculations you can do for that. And based on that, how much CO2 will be generated, what is the mass of CO2 generated, those calculations can be done. And then you look at the characterization of environmental impact. As you can see, solar lamp is much smaller than compared to kerosene lamp. Kerosene lamp impact is much higher, which the answer we kind of already knew, isn't it? It's not that we don't knew what's the impact, but here we can quantify how much is out of different categories. If you look at which one you see more, like it's a kerosene lamp is much higher than solar in most of the categories. So that's kind of gives you an idea, and you can then you can normalize it. If you normalize the data, you can see for most of it you don't see much impact in terms of the solar lantern, and but in the some you see more impact in terms of the kerosene lamp, which we showed up here. So 600 people already use kerosene lamp for lighting. CO2 produced is a 3.15 kg of CO2. For kerosene lamp, 1.638. So much higher. So it's we can save 252,000, like a million tons of CO2 if we use in terms of if we start using solar lamp as opposed to using the kerosene lamp. So how much environmental saving we can quantify. Again, for many of these exercises, you may say that, oh, I already knew the answer. That's true. You already knew the answer that which one is better, but you had the qualitative answer. What LCA exercise does is it gives us a quantitative number so that you can use that number and use it for better product design. So these were the two examples. In the next video, we'll look at another a few examples in the next few videos. And with that, let's close this particular video, and I'll see you again in the next video for this particular week.